Welcome to the Deep Dive. Today we're tackling quantum computing. It's this huge leap, really, a paradigm shift that looks set to redefine computer science and, importantly for many of you listening, software development. We're moving beyond the familiar world of bits, zeros and ones, into the strange world of qubits, superposition, entanglement.
Sounds like science fiction, doesn't it?
It really does. But the thing is, its potential impact on how we actually code and what software can even do, well, that's becoming less fiction and more reality in the making.
Absolutely. And look, you probably won't be debugging quantum code on your machine tomorrow, but getting your head around the basics, the principles, and what they could unlock, that's, I think, really crucial for any developer thinking about the future.
I agree.
This isn't just theory for physicists anymore. It's a fundamental shift with real potential for software.
Exactly. So, for all you developers, you tech-savvy folks tuning in, our mission today is basically to demystify quantum computing, give you a clear, hopefully easy-to-grasp overview of what this quantum revolution means for code. We've looked at a lot of material to pull out the key stuff for you.
Right.
Okay, let's dive in. Fundamentally, what is quantum computing? How is it so different from the classical computers we use every single day?
Well, at its core, it uses the rules of quantum mechanics, which are famously weird to process information. Classical computers, as you said, use bits, 0 or 1, on or off, simple state. Quantum computers use quantum bits.
Qubits.
Qubits. Okay, these are the stars of the show. What makes them so different from a regular bit?
The big difference, the first one to wrap your head around, is superposition. So, unlike a classical bit, which has to be either 0 or 1, a qubit can be in a combination of both states at the same time.
Both at once. How does that work? Think of maybe a dimmer switch instead of a simple on-off switch. It can be off, it can be on, or it could be anywhere in between, or even like a mix of possibilities simultaneously. It's probabilistic. For developers, maybe think about concurrency. Imagine one variable holding, somehow, multiple potential values at once, and the computation exploring all those paths kind of in parallel. That's a very high-level analogy for superposition's power.
A dimmer switch that's on and off.
Yeah, that's definitely a mind bender. Okay, and then there's entanglement. That sounds even stranger.
It is pretty strange. Entanglement is another key quantum thing. When you entangle two or more qubits, they become linked, deeply linked. Their fates are tied together, doesn't matter how far apart they are.
Linked how?
If you measure one, you instantly know the state of the other one. Instantly. Even across the galaxy, in theory.
This connection lets quantum computers perform really complex calculations. They have this incredible coordination, a speed that classical systems just can't match. It's like having tons of processors working together, but perfectly synchronized, instantaneously.
Okay, so superposition gives you this massive potential state space, and entanglement links it all together for like hyperparallel computation. So where does this get really interesting for developers? What problems can these things actually solve that our current computers struggle with?
This is where the potential gets really exciting. We're talking about problems that are currently just intractable, too big, too complex for classical machines.
Like what?
Well, the famous one is Shor's algorithm. It uses quantum properties, specifically Fourier transforms, to factor large numbers exponentially faster than any known classical algorithm.
Factor large numbers. That's the basis of a lot of encryption, right?
Exactly. RSA encryption, for example. Shor's algorithm basically breaks it, or could break it, once we have powerful enough quantum computers. That's a huge deal.
Yeah, no kidding. Suddenly things like post-quantum cryptography make a lot of sense. They're trying to get ahead of this.
Precisely. And then there's Grover's algorithm. It gives a significant speed up quadratic, not exponential, but still big for searching unsorted databases. Think finding a specific item in a massive jumbled list much faster.
Okay, breaking encryption, faster searching. What else? What other areas could this touch?
Oh, lots. Think about optimization problems. Finding the absolute best solution out of a bazillion possibilities.
Logistics, scheduling, perfect examples. Optimizing delivery routes for a huge fleet, scheduling complex manufacturing processes, quantum computers could potentially find much better solutions much faster than we can now.
Right.
And machine learning. Quantum algorithms might dramatically speed up the training of complex AI models, maybe even enable totally new kinds of machine learning we haven't thought of yet.
Faster AI, better logistics. Keep going. Where else might developers see an impact? Drug discovery, materials science, huge potential there. Simulating how molecules interact is incredibly complex for classical computers. But quantum computers are naturally suited for it. We could design new drugs, new materials with amazing properties.
Okay.
Finance is another big one. Optimizing investment portfolios, detecting complex fraud patterns, supply chains, energy grids, optimizing those complex systems, even agriculture, like designing more efficient ways to produce fertilizer, and medicine, personalized treatments, better disease modeling, data science, pattern recognition.
Yeah.
The list goes on.
It really sounds like it could touch almost every field. But let's be realistic, it's still early days, isn't it? What are the big roadblocks? What needs to happen before this is mainstream?
You're absolutely right. It's very early. The hardware is still, frankly, in its infancy. A massive challenge is just keeping the qubits stable, maintaining their quantumness. It's called coherence.
No coherence.
Yeah. Qubits are incredibly sensitive. Any tiny bit of noise from the environment, heat, vibrations, anything, can make them lose their quantum state. It's called decoherence. It causes errors.
So errors are a big problem.
Huge.
Right.
Quantum error correction is a major, major area of research. How do we protect these fragile states and fix the errors that inevitably creep in? And then there's scalability. Building machines with lots and lots of high-quality, stable, interconnected qubits. That's an immense engineering challenge.
Okay, so the hardware's tricky. What about the software side? Can developers just pick up their Python or Java skills and start writing quantum code?
Not really. Not directly. It requires a pretty fundamental shift in how you think about programming. The way classical languages work just doesn't map neatly onto how quantum computers operate.
Right.
So this has led to a whole new field of, well, quantum programming languages and software development kits, or SDKs.
Ah, new languages to learn. Okay, what are some of the key ones developers should maybe start hearing about or looking into?
Yeah, there's a growing ecosystem. Microsoft has Q#. It's designed to work well with Visual Studio, aimed at scalable algorithms. IBM has Qiskit. That's a really popular one. It's Python-based, open source, lets you build circuits and run them on simulators or their real hardware.
Okay, Qiskit, Python-based, that sounds accessible.
It is. Google has Cirq, also Python-based.
Good.
Focused more on the near-term, kind of noisy quantum hardware we have now. There's OpenQASM, which is more like an assembly language for quantum circuits. Rigetti has PyQuil, another Python library for their hardware. Penny Lane is interesting and focuses specifically on quantum machine learning, bridging quantum algorithms, and classical ML tools.
Quantum ML, wow.
Yeah. And then there are higher-level approaches emerging, too, like Classic, which tries to abstract away some of the really low-level gate programming, letting you focus more on the problem itself.
That's quite a landscape already. It definitely sounds like the software tools are evolving fast, too. But it also implies, like you said, a steep learning curve.
It does. It's not just syntax. You really need to understand, at least conceptually, the quantum mechanics superposition entanglement to design algorithms that actually use those features effectively. That's a big jump for many classical developers. And another challenge is integrating these quantum systems with classical ones. Most realistic applications, at least in the near term, will likely be hybrid. Some parts run on classical, some on quantum. Making them talk to each other efficiently is key.
So it's not about quantum replacing classical entirely, but more like a specialized coprocessor.
For many problems, yes, that's a good way to think about it. A powerful collaboration.
Which brings us to a crucial question for listeners, especially the developers. What can you actually do now? How do you start preparing for this potential quantum future?
Okay, first step, I'd say, is get familiar with the basic concepts. Superposition, entanglement, maybe quantum interference. You don't need a PhD in physics, but having that foundational understanding is really necessary to grasp how the algorithms work.
Right, some basic quantum literacy. What next?
Start playing around. Experiment with the languages and platforms. Like we mentioned, IBM Quantum Experience, Azure Quantum, Google's Quantum AI. With Cirq, many offer free access to simulators, sometimes even limited time on real hardware.
Get hands-on.
Exactly. Write some simple quantum circuits, run them. See what happens. Also, just stay informed. This field is moving incredibly fast. Follow the news, read research summaries, join online communities. There's a lot happening.
Okay.
And maybe, most importantly, think about your own work, your domain. Are there problems you deal with, maybe complex optimization or simulation or specific data analysis tasks where quantum computing might, down the line, offer a real advantage? Start identifying those potential use cases.
That's solid advice. Learn the basics, experiment with tools, stay updated, and think strategically about applications. You mentioned cloud platforms making this more accessible. How does that work exactly?
Yeah, the cloud is really democratizing access.
Yeah.
You don't need a multi-million-dollar quantum computer in your basement.
Hey, probably for the best.
Probably. Instead, you access these machines, or simulators, remotely via cloud services. The simulators run on classical computers and are great for learning and testing smaller algorithms. They get slow quickly as you add qubits, though. And it's useful to know there are different types of quantum computers accessible. There are quantum annealers, like from D-Wave. They're specialized hardware, really good for certain optimization problems.
Okay.
Then there are the gate-based quantum computers from IBM, Google, Rigetti, IonQ, others. These are more general purpose, running algorithms based on quantum circuits, kind of like logic gates in classical computers, but quantum.
Got it. Annealers for optimization, gate-based for more general algorithms, and we're seeing cloud providers like OVH Cloud getting involved too.
Yes, definitely. OVH Cloud, for instance, is making a big push, especially in Europe. They offer access through their cloud to various European quantum emulators tools like Felice, Callisto, Pulsar, Percival, MyQLM. These let you try out different quantum approaches.
Emulators, so like advanced simulators.
Oh. Yeah. Essentially, yes, simulating different types of quantum hardware or paradigms. And significantly, OVH Cloud actually acquired a photonic quantum computer, MosaicQ, from the French company Quandela. So they're investing in providing access to real, novel hardware too, not just simulation.
Interesting. So the access routes are definitely opening up, both for simulation and real hardware, globally and regionally. It's clear this is a major direction for software development, something we really can't ignore. Okay, let's try and pull this all together. What are the key takeaways for everyone listening to our deep dive today?
Okay, I think the first thing is quantum computing is fundamentally different. It uses qubits, superposition, entanglement. It's just a different way of computing than classical.
Right, not just faster classical.
Exactly. And this difference gives it potentially incredible power for specific kinds of problems, ones that are essentially impossible for today's best supercomputers. We're seeing a whole new ecosystem of quantum programming languages and tools emerging that developers can actually start exploring now. The potential applications are broad cryptography, optimization, medicine, materials, AI.
Right.
It could be transformative across many industries.
But we also have to remember the challenges. The hardware is still developing. Keeping qubits stable and scaling them up is hard. Error correction is a huge hurdle.
Absolutely. And there's the learning curve for developers. You need to think differently. Plus, we're still figuring out the best practices for quantum software engineering itself.
Yeah.
How to design, build, test this stuff reliably. We're kind of building the field as we go.
Yeah, learning from classical software engineering, but adapting it.
Precisely. But despite the challenges, things are moving fast. And importantly, access is getting better through the cloud and simulators. The barrier to entry for learning and experimenting is lower than ever.
Okay. So to wrap up, here's something to think about. Look at the projects you work on now or the tech areas you know well. Where might quantum computing, once it matures, fundamentally change things? Could it solve a problem you currently see as impossible? It might feel distant, but the groundwork is being laid right now. We really encourage you to check out some of the resources, keep learning about this field. Getting involved early, even just understanding it, could be a really significant advantage down the road as quantum moves from the lab into practical applications. Thanks for joining us for the deep dive.